So this is still a continuation of Lesson 8 on review of the cell size, and Part 2 would be the plasma membrane introduction. And today is really a review of what you should have learned and retained from your honors CP bio class. And so let's just assume that we don't remember much of anything. And I will begin with the structure of the plasma membrane. And the plasma membrane ends up being very important as far as how a cell functions and how it receives signals and how viruses get into our body and are able to insert their DNA. All is because of the plasma membrane. So in the plasma membrane, as a quick review, remember that we have heads and tails. The heads are a phosphate group, and the tails are lipids. And that's why it's called a phospholipid bilayer. And the bilayer, remember, like the biplane from back in World War I, where we had an upper and a lower wing and a propeller here. And your little pilot would be in there, and hopefully they would have tires that would work. But these were called biplanes because they had two structures to them. And so that is why they call the plasma membrane a bilayer. And not to date myself or anything, but back in the 70s when I was going through my undergrad program, they didn't even know about the bilayer yet. So it was just Singer and Nicholson, the two scientists, that really discovered it through what is called a freeze and fracture technique, where they were able to do something we can even do in the high school lab now, where we can freeze a tissue and take off thin layers with a microtome chrome tool that we have, and we have it in the lab. We could actually do the exact same thing that Singer and Nicholson's did back in the 70s, where they were able to take this view and prove that there were two layers and that there were heads and tails, and it made up the phosphate lipid, so phospholipid bilayer. And when you get that essay in the AP Bio, one of the things that gets so difficult for you when you finally take the test is that you have gotten some material, it's at the college level, and so you've received such advanced information. A lot of it you've already gotten in Honor CP, so it's not a lot harder than Honor CP. That when you get a very simple essay question, sometimes you forget to give the most basic term. And they grade the essays 1 point at a time off of terminology, vocab, and whether you can apply that. And I have read so many of the essays where students are given a very simple question on osmosis or diffusion, and the first thing they forget to put down is that the plasma membrane is semi-permeable. That is truly the one of the points that they're going to be looking at. So if you got any essay at all on the plasma membrane, the first sentence better say it's semi-permeable because it controls what allows in and out of that cell. And it's called the fluid mosaic model because if you look at a top view of this, these are the phosphate heads. They look like tiny little circles. And if you ever look at a mosaic tile, and if you get to go to see in the Middle East or Egypt, or I've seen some of the most amazing mosaic tile work on walls where they take little tiles and they make it into a large wall mural, and they can be just absolutely gorgeous. And so that's why it's called mosaic. And fluid is because the phospholipid pieces are actually waving back and forth constantly, and occasionally these can actually flip over. And in fact, that happens usually somewhere around once every 30 odd days again. So again, phospholipid bilayer. Some of the other structures in there that you may not remember are that these are given a little bit more solidified or a little bit more firmness due to cholesterol in there. So cholesterol is a structure that, and again, these are called rings in biochemistry. And if I draw out, and I'm not very good at this, if I had Tristan Archer here, he'd be much better at this for me. And so, again, I'm coming down to my points, and then I have one last square piece. And it's important for you to identify what cholesterol looks like because the course requires you to know two different structures look like, and one of them is cholesterol. That should be like this. One is cholesterol and the other is testosterone, and they're virtually identical to each other, only cholesterol has the little lightning bolt on top and testosterone does not. So you're looking for what these are called rings. You're looking for a 4-ring picture, and here you have the lightning bolt, and so that's cholesterol. And cholesterol is embedded in that semi-permeable plasma membrane to give stability. And that's one of the problems here. Let me put now my rest of my tails. I wanted that nice and fairly solid looking for you. So part of the problem is if you get an extremely high fever. So in a unsaturated fat, remember that unsaturated fat has no double bonds in the fat structure, where saturated has at least one double bond somewhere in its structure. So here we have a steroid cholesterol, and what happens is that it is like if you have a high fever, it's as if taking that nice solid butter and putting it in a pan and start warming it up on low. And within a very short period of time, that starts to liquefy. Even if you just left the butter, which is considered solid at room temperature, by the end of the day, or even within an hour or two, that very hard solid that comes out of the refrigerator, if you've left it on the counter, that is already starting to soften a little bit. So that's what happens when our body gets a fever. All of our fats start to soften up. And at one point or another, it's the point of no return, where the person maybe could survive, but they're definitely not going to be the same person. We would have had too much liquefying of lipids that are in the brain and other tissues of the body. That's why that high fever, a child's body can tolerate 104 fairly well. An adult at 104.1 can no longer tolerate that very well and needs to be hospitalized. So this is cholesterol for stability. It makes that so it just doesn't fall apart. And then embedded within the plasma membrane are all different kinds of proteins, and these are channel proteins, all 3 that I've drawn here. And I've drawn 3 different types of channel proteins. And what is more is if I have this, now if I draw a top view of my phospholipids, on top of that you're going to find a variety of things. You're going to find glycoproteins and glycolipids, and these proteins would have been manufactured at the ribosome and then would have gone to the Golgi apparatus and got it that and received that additional piece to it to make it, instead of just a plain lipid that would have been made in the smooth endoplasmic reticulum, it now is going to be a glycolipid or a glycoprotein made at the side of the ribosome. So let's take a quick look at the different types of channel proteins and why we have them. So the channel proteins have a variety of reasons. These are embedded proteins. And again, the steroids are one of those embedded pieces in that. We could have glycoproteins, glycolipids. And they allow things in and out based off of what the polarity of the material. So materials can be hydrophilic or hydrophobic, and they can be polar or non-polar. And they could be polar charged or polar uncharged. And so review what polarity means. It's in your textbook. It talks about water is polar. And so here we have a ion channel, and I have drawn the one that comes up most commonly in this course, the sodium-potassium pump. And you did go over that in CP Bio. Again, that might be a vague thing for you to remember. But this needs a control factor, something we need energy for this to open up. And so that we're going to talk about in our next lesson is all about passive transport and active transport. And since this needs energy to open up, that is active transport. But again, I will spend an entire lesson just on passive and active transport, osmosis and diffusion. So here, if the body needed to get rid of sodiums, we would need 1 phosphate off of ATP to open up this channel. The sodiums have very specific spots to be in that channel, and then they're released, and 2 potassiums come and take their place. So that's an example of an ion-gated channel protein, one very specific, and it's called the sodium-potassium pump. Here would be another one that I could list, and that could be an aquaporin. and an aquaporin only lets water in and out. And water is strange in that it is uncharged, it is polar, it is uncharged, it doesn't have ions, and so it can actually make it through the plasma membrane without needing the channel protein at all. There are a few things that can make it through without needing the channel protein, and that is water, nitrogen, oxygen, CO2, and estrogen and testosterone. So these are steroids. And so the problem comes if I tell you, okay, so water can make it through in and out of that plasma membrane. It is uncharged and it's polar, so it's allowed in and out. So why does it need its own channel protein? Well, the reason for that is it takes a long time for it to diffuse that way, and so it really needs that aquaporin. And I will try to find a picture of cellulitis for us. And so if a person is retaining a great deal of fluid for whatever reason, they are going through chemotherapy, or they could have an infection somewhere in their leg or their foot is very common. What happens is that an awful lot of fluid is building up in that area, and the leg or the foot starts swelling and will turn purple colored even. And eventually fluid, the water actually, or the saline from the water and our natural salts, starts leaching out of the skin. You can actually see fluid out of the skin. And that's when it's being forced through these plasma membrane in places that we would not expect it to be forced out. So aquaporins are just for pure water. And then I could also have another one over here. Let's put one in here. That's just for glucose. So we have a variety of them. This one here is called it's a integral, or from one side to the other, plasma membrane. But this one is sort of strange in that it is called an integral plasma membrane. And you'll see it in these helixes or these curlicues, and they come in groups of 6. And so your textbook does not show what we call the receptors at the top of this. So oftentimes we have a channel protein that is not for allowing fluids in and out, but for signaling. And so, for example, in this one, if I have an issue where I have an awful lot of glucose in my body, let's say that I'm that 8-year-old child and I've gone to that birthday party and I've stuffed my face full of every candy. I'll remember my niece. My niece, Krista, lived with me actually for 5 months while she was house shopping, and she had her 2 little girls with me. And I remember after they found their home, at their first birthday party after leaving, they had a candy bar. And I was thinking to myself, oh my, how could this go wrong? You're giving 4-year-olds free rein to an entire candy bar, and what could go wrong? Well, of course, their behavior deteriorated quite quickly because they ate all the sugar, and there's too much sugar in their body for their pancreas to even tolerate it. And so they had a sugar high, and the sugar high is uncontrollable laughing and behavior that we would not consider to be appropriate for children. And part of the problem is the integral proteins simply couldn't keep up with the sugar overload of those poor children. And so what was happening is the pancreas is releasing insulin, and the insulin goes to the integral protein, especially if it's like in the liver. We would have an awful lot of these in our liver tissue. And so the insulin says, you need to store glucose, and you need to store it fast. And so the message goes here, and then the message goes through the membrane and into the inner part of the cell where it says, store glucose as glycogen. And, it takes, unfortunately, a little while to do that. It's not instantaneous with children. So we had an awful lot of sugar high. If you take anatomy when we are studying lysosomes, and it could be that I could give that an assignment for you. There's a video that we watch, a movie that we watch, where the children had a digestive disorder and could not get this out of their muscles. And so that was, they were deteriorating. So that's the quick overview of the plasma membrane. I would take the time, I would go over the chapter and take a look at that. The next section, we're going to spend some time on the functioning of all of these proteins. Thank you.